Question 3 reads, a racetrack has the shape of an inverted cone, as the drawing shows. On this surface, the cars race in circles that are parallel to the ground. For a speed of 25.0 meters per second, at what value of the distance d, and that's the distance up the ramp, should a driver locate his car if he wishes to stay on a circular path without depending on friction? What's key in this question is that we don't want the car to have to depend on friction. And in fact, it sort of simplifies our analysis a little bit. Let's get to a diagram and look at how this is done. Okay, I'm going to draw a diagram with an inclined ramp, and my box represents the car on top of that ramp. To that, I want to add the numerical information. First off, we know that the inclination of the ramp, theta, is equal to 40 degrees. As well, we know the speed of the vehicle. The speed is 25.0 meters per second. So based on that information, we can now start to construct a free body diagram. So what we understand is that the vehicle is traveling at the right speed and the right distance so that friction doesn't come into play. So our free body diagram actually is fairly easy to draw. First of all, we'll add naturally what acts at all times, the force of gravity. And the second force that we would add to that diagram would be the force of the ramp pushing up on the car. Of course, it is tilted due to the fact that the ramp is inclined, and so we have our normal force pointed this way. Now, what makes sense at this point is to resolve that normal force into a vertical component, so a component that's parallel to FG, and a horizontal component that points to the center of the cone, or towards the axis, or at right angles to the axis of the cone. And those would look like this. And so my vertical component I'll call vector Fny, y being the up and down direction, and my horizontal I'll call vector Fnx. Now, the last thing that I'll add to my diagram are some distances. So I'll add the distance up the ramp and also the radial distance, or the distance the car is from the center of axis, or the axis of the cone. So those will be marked D and R. And now we can start our analysis. What we understand in this problem now is that the net force is just the centripetal force. This car is traveling in a circular path without the assistance of friction, meaning no friction is holding it from sliding up the ramp or down the ramp. So all we have is that net force, that centripetal force, that is causing the car to travel in its circular path. So in fact, we can deduce from that F and X, vector F and X, is equivalent to the centripetal force. So those are equal to each other. And so from that, we can also conclude that the vertical component of the normal force, vector F and Y, if we look at that magnitude, that has to be equal in magnitude to the gravitational force, so vector F, G. So when we look at the magnitudes of those two forces, they have to be equal. Well, that leads us very quickly to the fact that vector F and Y, the magnitude of that is simply calculated by doing this, the mass of the vehicle times G. And in this case, I'm just going to call G positive because we're talking about the magnitude of the force. All right, moving forward from that, if we were to look at the ratio of vector F and X, again, the magnitude over vector F and Y, I think you could argue pretty easily that that is the tangent. That is the tangent of angle theta. And so now we very quickly have this relationship. The vector F and Y, vector F and X, the magnitude of vector F and X is just simply vector F N Y magnitude times tan theta. And substituting, we get that that must be, in fact, mg tan theta. I'm deliberately doing these in multiple colors for you because it relates to the color of the forces in the diagram. So we have that relationship that the magnitude of Fnx is equal to mg times the tan of theta. So now we can go directly to our centripetal force, and we can say our centripetal force is this. It's equal to mg, and I'm now just going to stay with the yellow, tan theta. Now, we also know that centripetal force is defined this way. We know that it is m v squared over r. And so, using that in our relationship, we have mg tan theta. I'm going to just divide out my m's, so it's mass independent. We don't really care what the mass of the vehicle is, so this could be a 500 kilogram really fast stripped down vehicle, or it could be a 1,000 kilogram heavier vehicle. The solution to this will be the same. It will remain the same. Now somehow we're going to try and bring d into this. And so I use this relationship that r divided by d is my cosine of theta from my diagram. So r is in fact equivalent to d times cosine of theta. Well, substituting that into my expression, I have this. I have v squared now over d cos theta is equal to g tan theta. So finally, taking this up here, now if we rearrange this equation, we get that d is equal to v squared over g tan theta cosine theta. And that is simply v squared over g sine theta. Now substituting in our values, we have 25.0 meters per second squared over, I'm not sure what you're using for gravity, I'll use 9.81 meters per second squared times sine 40 degrees. And if I work that out on a calculator, I get 99.2 meters. Everything was given to 3 significant figures, so our final answer will be rounded to 99.2 meters. And so therefore, the car needs to position itself (99.2 meters) up the ramp. That's all there is to it.